to. You like science, but math is there, I'll do it. But you will love calculus because you get to see why you have done all that weird math stuff and how it connects to your science classes. The cool thing about calculus is it takes motion into account. Do you remember in Algebra 2 how you would work a problem with a ball thrown in the air and they're like, there's no wind or wind resistance, like we're in a vacuum. And,
not real life.
Right, we don't have to do that anymore. Calculus gets to take in some other things into account. It's really exciting. Now, there are three big concepts that we're going to talk about. Today, we're going to break down what a limit is. A limit is what allows us to take into account motion, to stop thinking about stationary things. Limits involve infinitely large and infinitely small quantities, and that's why it took so long to figure calculus out, because people struggle with that concept of infinity. It hurts our brains sometimes. So that's why it took so long for calculus to be discovered. You probably have heard of Isaac Newton. He was kind of a big deal.
Who's that?
No, not important. He only developed calculus, but good question. Okay, so that's the first concept we're going to learn is a limit. The second concept we're going to learn is a derivative. So limits will be Chapter 1, Unit 1 in Calculus. We'll spend about 3 weeks on limits. It won't take too terribly long to break down that concept. Derivatives, which you'll notice eventually will come up here. Derivatives are a slope of a curve at a point, or instantaneous rate of change, which you can, those of you in physics can imagine why that's important. Instantaneous rate of change allows us to look at stuff that's happening right now. For example, if I'm driving from here to Fort Smith and a cop pulls me over and I say, I just averaged 55 miles an hour, he's going to say, I don't care. Right now you were going this stuff, right? That he doesn't care. It doesn't matter what I was averaging. And so up until this point, you've never been able to find instantaneous rate of change. You could just find average. So that'll be the derivative concept, a big deal. And the third one is definite integral. You won't see that until next fall, which involves area under a curve. So those are the three big calculus concepts. Today we're going to talk about limits. So we're going to talk about them numerically and graphically today. That will only take us a day to talk about. Tomorrow we'll start talking about them algebraically, and that'll take a little bit more time for us to break down. So, graph the function. As x gets close to 2, what does f of x do, was the question. So let's answer the easy part of that question first. Graph it. How do you do? X squared moved down 3. And we can plot as many points as we needed to. Normally 2 to 4, so if we move that down through to have this graph. Everyone agree with that? Then it asks me a very strange question that I've never been asked before. As x gets close to 2, what does f of x do? First of all, what in the world is f of x? That's y. So as x gets close to 2, what does y do?
Increase.
I don't know, let's look. As x gets close to 2, what does y do?
It's the 1.
It gets close to 1. Do we agree? As x gets close to 2, y gets close to 1. You just did your first limit. What?
Blow my mind.
So that's what we're going to be looking at today. So, what is the limit? This is not the real definition. We'll look at the real definition in a few days. The real definition is scary. So this is my definition. I made it up. The limit of a function is the y value, or the height that the function approaches as x gets closer and closer to a specified value. You can imagine why this is not the actual mathematical definition. Closer and closer is kind of a relative term, right? So there is an actual mathematical definition, but for you and for today, we're going to use this one.
So basically just looking at figure out the coordinates.
Maybe. Maybe. We got a lot to learn. This handout that I'm passing out is a notes page. It's just going to keep you from having to draw a bunch of graphs later. It is not homework, it's part of your notes. Grab one and then pass it back to you. So the limit of a function is the y value that the function approaches as x gets closer and closer to a specified number. So the question about a limit is, what is y doing when x is doing something? What's happening to y when something is happening to x? So we're going to look at limits three ways. We're going to look at them graphically, numerically, and analytically. Today, we're going to look at them just graphically and numerically. Analytically is algebraically doing them without a picture in front of you. And we will look at those starting on Monday, but we'll spend several days on analytically. Before we get started, we have some notation. The notation for a limit is the limit of f of x as x approaches a. So this piece right here is notation for the limit of f of x as x approaches a. And you can see I have that how to read it out to the side so you don't sound silly. It's the limit of f of x as x approaches a. If you put a little plus sign at the top of that A, then that means we're looking at what's called a right-hand limit, approaching only from the right-hand side. So that's read the limit of f of x as x approaches A from the right. So that's a right-hand limit. We're approaching an x value from the right-hand side. And then the last one, as you can imagine, if I put a little negative up there, it's from the left. Why do you think they use a plus to do right and a negative to do left?
Positive side and
Yeah, from the positive side and from the negative side of the graph. Makes sense. Mathematicians are pretty logical most of the time. This is the notation for a limit. We'll look at this a little more in depth once we start looking at pictures. But there are times that limits don't exist, when we will say the limit doesn't exist. One of those times is when the left and right-hand side of a limit approaches two different numbers. If f of x increases or decreases without bound, example, vertical asymptote. So if we have a vertical asymptote, as we approach that vertical asymptote, we would have a non-existent limit. And the last case, you can write it down, you'll have to see a picture before that makes sense. But if f of x oscillates between two fixed values as x approaches c, immediately people will say something like a sine graph, but it's actually more complex than that. A sine graph has limits everywhere, it's fine. It's something crazier than that. We'll look it up.
Does it make it look like a sine graph line just sticking an x squared or something?
1 over x, actually. Sine of 1 over x is the crazy one. As x approaches 0, it just bounces off the place. We'll look at that later. So, 3 places when limits don't exist. I think it's on the next slide. I have a little video that's going to come up that does a really good job of explaining limits.
Now you have some idea of what a limit is, and we need to talk about when does a limit exist. To illustrate my point before we get started, let's set up an example. Let's say you and a friend are going to meet for dinner, and you're meeting at a diner that's centrally located between the two of you. If you live east of the diner, and your friend lives west of the diner, and you both want to drive to meet there, ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right, or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side towards some specific value of x. As long as that function meets in the middle, as long as you arrive at the diner, as long as the heights from the right and the left are the same, then the limit exists.
Yes, it gets better.
Now it's time to get down to the brass tacks and look at this mathematically. Take a look at the graph of this function f of x. Visually, you can see that it's got a break in it at x equals 4. So, if we travel towards 4 from the right, we will arrive at a height of 2. However, if you travel towards 4 from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4. Let's go back to our diner metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We won't both arrive at the diner, and no limit exists. We call the height at which we arrive from the right the right-hand limit of f of x, as x approaches 4 from the right. And we denote this with a little plus sign in our limit symbol. Our height that we arrive at from the left is called the left-hand limit of f of x, as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for a limit to exist, both the right and the left-hand limits must be equal.
Okay, so that's a big deal. For a limit to exist, both the left and right-hand limits have to be the same numerical value, have to be the same number.
Now let's change this function just a little bit. This new function, we'll call g of x, does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrived at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the graph. because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point, coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value.
Okay, so some big important concepts were there, and I know that I could show you those, but the diner example is just so good. It gives you that visual of what we're talking about. A limit is not what the function equals. And that's a really big misconception. I told you what a limit was at the very beginning of class, and someone immediately said, hey, can't I just plug it in and find the answer? Maybe, if there's a number there. But it turns out you can have a limit sometimes even if there's not a number there, like at a hole. You can see why we just reviewed holes and vertical asymptotes probably, because those are going to be important algebraically. So a limit exists at a hole as long as from the left and the right you approach the same thing. A limit is all about what you're approaching, not what you are. So that's what we'll keep in mind. Okay, so example, and I think you have this on your picture. That was my goal. That way you didn't have to draw it. Okay. And I want to go through and find some limits, function values, kind of take some of the mystery out of this whole limit thing. So this is how you find limits from a graphic. So the first question is, what is the limit as x approaches 0? As you are new at this, you're going to take two fingers, go close to 0, put them on each side of 0. For my video, I'm going to put little dots on each side. Right? So I'm going to set my fingers on both sides of 0. And I'm going to walk closer and closer to x equals 0, and I'm going to ask myself, what is the y value approaching? And some of you already said the answer, and you were perfectly right. What is it? 1. From both sides? Yes. The next question is not a calculus question at all. It says, what is f of 1? Have you been asked that question before? Yes, and how do you find it? You go look at 1, you ignore everything around it, you just look at 1 and find where the dot is, right? Find where the point is. And at 1, do you agree it's at 4? Mm-hmm. So that's what this notation means. This notation is not a limit. It doesn't matter what's going on around it, it's just what it is. The next one is the limit of f of x as x approaches 1 from the left. So I'm coming in from the left hand, coming in from the negative side. From the left, what do I approach? I'm going too fast. The limit is x approaches 1 from the right. Negative 2. Everyone agree with that? So take my hand to the right of 1, find where the graph is, follow that in to the point. And then I look at what is the y value. Negative 2. Any questions before I keep going? So the limit from the right was negative 2, and the limit from the left was positive 2. What does that mean for the limit? There's not one. And the notation for that is D and E, which stands for
Does not exist.
Does not exist. There is no limit there because from the left and right, we approached two different things.
We always use 0 with a slash, right?
For limits, right, D and E. For undefined, that's good. You can write no limit. Be familiar with D and E because on the AP exam they will use does not exist for that. Okay, let's look at the next one. The limit is x approaches 5 from the left. Okay, 5 is over here. Why do you think it says from the left?
Nothing to the right.
There's nothing to the right. If it asks from the right, I'd have to from the right because there's nothing to the right to approach from. From the left, what am I approaching as x approaches 5? What is f of 5? Nothing, and so just quick, nobody's probably going to count anything off for you doing this wrong. Just mental note, the notation for that is the normal undefined. That point's undefined. Again, nobody's going to count off if you do that incorrectly, except maybe a college calculus professor. But there is a difference between a limit not existing and a value being undefined. Quirky math people. Any questions about that one? You have the next picture and the next questions on your graph. I want you to try them all. See if you can answer those questions. And it is okay while you're doing this, use your fingers. How long did that just take you to answer all those questions?
Typically, they're wrong. It's 1, 2, 20 questions. There are way more than 20. There are way more than 20.
Okay, everyone with me? How many of you, has anyone not had time to answer them? Okay, let's go through them together. X approaches -4. So, as X approaches -4, what does Y approach? 0? Everyone get 0.
65.
Any questions about that? As X approaches -2. +4. Does everyone agree with that? I had a hole there, is that okay?
Yes.
Yes. I know the video took a very dark turn. I don't know why they had to burn that one down, but whatever. It worked. It makes sense. I didn't make a video. That's what it takes for you to understand calculus. The diner can sell that. F of -2. What is F of -2? -1. Why -1?
That's where the point is.
That's where the point is. Good. Okay, I'm going to skip that one on the left and answer the 2 on the right. How would I answer these 2 first? They're easier and they're going to help me answer that one because it's not the same and that one doesn't exist. So let's look. As I approach 2 from the left, -4. 2 from the right. How do you know? Those 2 numbers are the same. If they're anything other than the same number, then that limit does not exist. What is F of 2? -2. How'd you get that? So how we do it? First topic of calculus. How do you not get it?
one.
Now, a lot of times, especially on the AP exam, when this is a one-question deal and they only ask you one question, sometimes you look too quickly. They can trick you. At first glance, everybody sees the break in this graph, right? You're like, doesn't exist, doesn't exist.
We need the following students to report to the library: Nicole Phillips,
Negative 1.
Brooklyn Rosentater, Maggie George, Ashton Spitzer, Addison Graham, Connor Hadley, and Adelaide Lawson to the library at this time.
Negative 1.
There is a limit as x approaches 2, correct? So I wanted to point that out because sometimes people will get so quick at these, you'll pick out that break and go, oh, it doesn't exist, let's say break. Be careful about where the break is. Make sure you pay attention to what x value you're approaching. Does that make sense? No? Okay, so as x approaches 2, what is y approaching? Do you see that? But as x approached 3, it was 2 different things, and that's where the limit didn't exist. So it does matter where x is approaching on whether the limit exists. X approaches negative 4.
Negative 1.
Negative 1. In fact, anywhere from 3 back, right? Or 3 forward, we can find a limit. It would all be 3. So we can find this one is negative 1. Okay, let's look at this one. Look at 2. What's the limit as x approaches 2? Are those sometimes the same answer? Yeah. Quite often, I would say, when are they not the same answer?
There's a hole.
When there's a hole or a break or something weird like that, right? So on a nice, normal, smooth, continuous, I'm throwing that word out there, we don't really know what it means yet, but graph, then it would make sense. The function value and the limit would be the same.
We don't know what continuous means?
You have an algebra 1 definition. You can draw it without picking up your pencil. As you can imagine, that is also not a mathematical definition. But we'll work on that. We'll learn the real one in calculus. The reason you don't learn it yet involves calculus. Alright, the limit as x approaches 0.
3.
Negative 2.
0.
Hey, any questions about that one? I'm going fast, but slow me down. If there's ever one that you, if I don't, I'm looking for the faces, but if I don't see it, you let me know. Yeah, it's funny how I look. Look at this one. F of negative 2 is undefined. Do we agree with that? What's the limit as x approaches negative 2? Does not exist. Now, something we can do, and this one didn't ask, but I do want to go ahead and answer it. Sometimes they will ask for a left or a right-hand limit around an asymptote, and we could answer positive infinity or negative infinity. So if I were asking the limit as x approaches negative 2 from the left, negative infinity, because I'm going down. And from the right, we would be approaching positive infinity as x approaches negative 2. So we can answer with plus or minus infinity. And the limit as x approaches 0.
3.
3.
Oh, yeah.
As x approaches 0, what does y approach?
3. I see.
So if you get stuck, what do?
Draw your fingers.
Put your fingers on both sides of the point. Walk yourself in. So it's x approaches 0. As x approaches 0, starting at 0. I'm going to put my fingers on either side of 0. Approach. Approaches 3. The limit is x approaches 3. There are 2 answers, and different calculus teachers are picky about different ways to answer this. want you to say do not exist. And there's a reason, and it involves the actual formal definition of a limit, and we'll talk about that later. But remember, when do limits not exist? What were the three cases?
Holes, asymptotes, breaks.
Increases or decreases without bound. Would you agree infinity is not a number? So infinity and infinity are not necessarily the same. Could you have different levels of infinity?
Yes.
I mean,
No, there's infinity plus 4.
and infinity times infinity.
Or infinity, square infinity. Oh, I got you.
I'll show you some.
You ever seen that one? That was great.
The AT&T.
Oh, have you seen the
I'll show you it. I have it on a slideshow
Have
somewhere.
you seen the
Oh.
commercial?
So anyway,
Yeah.
I'm going to answer does not exist. AP will also accept negative infinity, so I will take both as well. So we won't get too caught up in that conversation. However, if those were going the opposite way, what do we have to say then? We have to say does not exist because a negative and infinity and positive infinity are not both going to exist, right? So, again, good calculus teachers prefer does not exist, but the AP exam accepts it. And F3 is 1. Okay. Any questions about that one? I'm just teasing
Okay, go back.
about that. So if you have a friend that's at some other school and their calculus teacher does it the other way, I'll have their teacher.
Oh, I didn't see the dot.
Yeah, so they filled it in.
See, this is why I want to say
Okay. Numerically, everyone get a calculator out.
oh my gosh.
Oh my goodness. Are you gonna make it?
Don't.
I can do it. So we're gonna talk about limits numerically. Remember, there are three ways we can look at limits. We can look at them graphically, numerically, and algebraically. Numerically is literally using your table to get closer and closer and look and see what y is doing. Today, both approaches to limits are very elementary maybe. But we will get into a little bit more fun stuff tomorrow. But okay, so if you will go to your y equals and type this function in your y equals. You could look at it graphically, but we're going to look at it numerically. What is this good for? Well, if you come to a limit you can't do algebraically and you happen to have a calculator, you could do it numerically. So type x cubed plus 1 divided by x plus 1 in your calculator. Then I want you to go to second window, which is your table setup. I don't know if we've done this in here or not. Have we done this before?
Yeah.
Put your independent variable on ask. That allows me to type in my table. I don't have to scroll a bunch. I'm lazy. But you can do it other ways. But that way you can type in your table. Then go to second graph, which is your table. If you want to delete everything out of it, you can, or you can just type over what's sitting there. So I want to type in some numbers that are getting close to -1, because that's what I want to know. What is the limit as x approaches -1? Why is that going to be a possible problem? Random thought.
Because it's a whole or an asymptote.
It's either a whole or an asymptote. How do you know?
Because it's undefined.
Because it's got a 0 on the bottom. So I want to know, what is it? Is it a whole or an asymptote? And if it's a whole, what is it getting close to? And some of you probably already know how to do some of these algebraically if you think it's ahead, but
Yeah.
it is a whole, isn't it? Okay, so what getting close to -1 from the left.
Negative.
-1.1. So I put this table here, you can kind of see it, but you can see where I got those numbers. And when we talk about close, we want to be really close, not like -10. We want to get really, really, really close to -1. So I did -1.1 because couldn't the function jump up somewhere else? I want to know what's happening right next to -1. So I did -1.1, -1.01, -1.0001. Could I keep going? Yeah. Right, we can do this all day long, right? So if you can tell from these three, you could get closer. Okay, so what do you type in -1.1?
3.31.
3.31.
What do you type when you type?
3.036.
3.030.
0.0301?
The next one is 3.03.
3.03.
Now, I could keep getting closer, but what does it appear that it is approaching from the left?
3.
Because I keep adding in those zeros, right? So it appears that from the left, if you can't tell, keep putting in more zeros. Okay, now let's go from the right.
Point.
-0.9.
2.997.
2.997.
Oh, no.
Oh, no.
2.7.
2.71.
You did it backwards.
You did it back.
2.97.
Yours.
2.997. And those of you who are good at patterns, what do you think the next one would be if I put in another
0.9999.
Don't you think it'd be another 9?
I think you said too many nines.
I did say 3.
What is, and we know this is a line, you know, I can't find that. What does this appear to be approaching from both sides? 3. That's how you do a limit numerically. You just type in numbers, get closer, to see what's happening.
This is a limit.
You still put
You put
undefined though with
undefined.
-1?
You put undefined.
At -1, this is a table. This is a limit.
Oh.
The table.
You put undefined.
You try it in your table. What do you type?
Error.
See? Undefined.
So that's your limit? Like,
Probably. Probably. But technically for a limit, you need to look from both sides. Okay, now the last one, you knew a little bit more about what was going on because it was algebraic. You saw that 0 over 0, which, and if you remembered how to factor x cubed plus 1, you probably even could have factored that sum of cubes. This one is a trig function, so it's a little harder to visualize. But I want to approach 0. I want to do it numerically. What table? This time I didn't tell you the table, so you got to tell me what's close to 0.
1.1. 0.001.
Okay. Which side of 0 is that on? The numbers Drew's giving me.
Right side.
It's to the right. So he said 0.1, 0.01, 0.001. I like it. I agree.
-0.1. -0.01. -0.001. -0.0001.
Good.
1.
Does everyone agree with that?
Yes.
If you are having a hard time figuring out what numbers are close, add or subtract those numbers from the number. Right? Add 0.1, subtract 0.1. Sometimes it's 0.9 that's close. Sometimes it's, if you're around 0, it's 8. So we'll look into that one that's at 1 in a second. Okay, add those numbers in.
Mm-hmm. Michael, you know what I see your opinion?
I did.
You look nice.
Hey.
Oh, Lord.
Okay, what do you get when you type -0.1 into that function?
986.
What about 0.01?
Project 3.
And 1.999 again, like 4 nines. If you can't tell what it is, push your arrow to the right, and you can see all the decimal places. need to keep getting numbers closer and closer and closer. If it doesn't end up doing anything that's a pattern, there's a good chance you got a non-limit answer. Do you know what I mean by that? You don't see it approaching something. This one, clearly, we're adding more nines.
Will we ever approach limits at this point?
More and more decimal places. If you start, like, if it's 1/4, your calculator will say, at first it'll be like 0.24, but then it'll be like 0.249999. And you're like, oh, that's probably 0.25, which is a 4. So, if you put enough in there, you can see it. There, if it's approaching a third, it'll keep tacking on 0.3.
Put it in your finger. Yeah.
Zeros and
Yes! Calculator is always in radians and calculus from now on.
I know, I'm getting wrong
It's a good question.
zeros and 5 is get 5 is
Okay. Are these also 1.999?
Yeah.
Does that look right? Something like that. What are we approaching from both sides? Let's look at the next one. Letters and number. Mainly at this point, I think you've kind of got the gist of how to work the table. I just want to make sure you could even set the table up. What would go on my table if I'm approaching 1?
1.1 or 1.1.
Okay, so on the right-hand side, do we agree 1.1, 1.01, 1.001, or as many zeros as we need? 0.9, 5.9. One of the most common mistakes on table problems is people will do 0.01. That's close to 0, not very close to 1. So be careful about that. Any questions about that? You plug them in, see what you're approaching. Someone do this one real quick. I think it's a fraction. Is it 0.6 and then 0.66? So this one. Start tapping on 6s after that. Do you see what I mean? Because Drew asked this question. It's a good question. How do you know if it's approaching a fraction? Again, you should see a pattern. You should see a pattern show up. So that's numerical derivatives. You have your worksheet. You will need a textbook to do numbers 1 or 16, 18, and
number 9.
oh, I agree. Okay, so everyone listen for me. On number 9, the letters at the bottom of number 9 are A, B, C, and D. On the graph, do you see those letters A, B, C, and D? Okay. Number 9, start at the left-hand column. A from the left. The F, the first one, is A from the left. The second one down is A plus, just A. It's not plus or minus, it's just A. Labeled as expert is A. Then it's B from the right. Then it's C from the left. C and D from the left. Okay, then other column. It's the top one is A from the right.